Hello and welcome to this Automotive IQ webinar by Hamamatsu. Before we start, we have 3 questions we'd like to ask our audience, so please take 10 seconds per slide and give your input. Thank you for your feedback. I will now hand over the microphone to Slawomir and Piatek, who will take you through the presentation.
Good morning, good afternoon, and good evening, everyone. Wherever you are, thank you for logging into this webinar. My name is Slawomir Piatek. I am technical consultant for Hamamatsu Corporation. In addition, I'm a physics lecturer at New Jersey Institute of Technology. We are going to spend the next 60 to about 1 hour discussing a LiDAR, in particular, Time of Flight LiDAR. There's a great interest in automotive industry to develop systems that make driving safer. In addition, the automotive industry is interested in developing self-driving cars. Such systems and such self-driving cars must have ability to determine a 3D map of its surroundings, i.e., we have to have ways of measuring a distance. It is likely that there will be 4 technologies involved. Sonar to measure short distances, Stereovision, radar for larger distances, and as I'm going to argue in this webinar, there will be need for LiDAR, which is acronym for light detection and ranging. As mentioned already, this webinar will emphasize time of flight LiDAR, and time permitting, I may spend some time discussing frequency modulated continuous wave LiDAR. The outline is as follows. So first, I'll discuss the basic concepts of time of flight LiDAR. Then, we'll discuss the challenges in designing a realistic system. Then, I'm going to review the basic types or designs of time of flight LiDAR. By then, we are going to get the idea that designing such system is quite challenging, very difficult, and perhaps it may be a good idea to use some other concept, like frequency modulated continuous wave LiDAR. And we're going to end with mandatory summary and conclusions. Let's begin with the basic layout of time of flight of LiDAR. First, we need the source of light, a laser, for example, that produces short duration pulses. The laser emits light, and at an instant of emission, a start pulse is generated either by laser itself or by dedicated photodetector that siphons some of the light emitted by the laser. The pulse propagates towards the target, reflects from the target, and some amount of light, as we shall see later, very little light generally, is going to return. We are going to collect this light with collection optics and illuminate a photodetector whose output response is going to provide a stop pulse that is going to deactivate an electronic clock. The electronic clock measures the time of flight delta t, and thus one can quickly calculate the distance to the point of reflection. Just to give you an idea, if the range to the reflection point is about 100 meters, delta t, or time of flight, is only about 0.7 microseconds. An increment of 1 meter will correspond to about 7 nanoseconds in time of flight. We are going to measure very, very short time duration, which will generally mean that electronics involved in time of flight LiDAR will have to have a large bandwidth. Let's now discuss uncertainties. First, we are going to consider a case where illumination spot on the target is much smaller than the features of the target. If this is the case, then uncertainty in the distance, delta sub r, is primarily due to uncertainty in measuring delta t, which will mostly come from jitter in the photodetector plus electronic jitter. However, if the beam or if the pulse is divergent, i.e., the area that it illuminates or the features of the target are smaller than the area of the spot, then there is another contribution to distance uncertainty, which comes from the width or length of the pulse given by speed of light times the pulse duration. Here, we can make a first conclusion that it is highly undesirable to have divergent pulses in time of flight. First, there is additional contribution to uncertainty, but also it worsens photon budgets. It is therefore critical that emitted pulses are collimated as much as possible. However, no perfect collimation is possible due to laws of physics, diffraction. If I have emitting elements of diameter d, emitting radiation of wavelength lambda, then there will be diffraction, which is linearly proportional to the wavelength and inversely proportional to diameter of the emitting element. There is a beam divergence inherent in these systems. That beam divergence then will cause, there will be a limit on minimum resolvable transverse size at some distance r, as shown in this diagram. It is this beam divergence that is going to cause us to use some form of LiDAR in the future self-driving cars, as supported by this example. Suppose I use radar with frequency of 77 gigahertz. That corresponds to a wavelength of about 0.3 centimeters. Let's take an optimistic size of antenna of 20 centimeters. The diffraction equation implies a divergence angle of about 1 degree, which implies uncertainty in transverse resolvable size of 2 meters at about 100 meters. Please note that this minimum resolvable size is distance dependent and to increase with distance. So what this means is that if I have 2 trees 100 meters away from me and they are 1 meter apart, this radar would not be able to tell them apart. However, if instead of radio waves I use light, say 1550 nanometers, with a diameter of emitting element of 5 millimeters, then in this case the divergence of the beam is about 0.02 degrees, implying uncertainty in transverse size of about 3.7 centimeters. One can therefore conclude that if one desires high-resolution 3D map, where the transverse resolution is on the order of a few centimeters, one will need some sort of LiDAR on the future self-driving car. Let's now discuss timing of our LiDAR. So first, I would like to point out that to produce a 3D map, we have to steer the beam. In other words, pulses must be emitted at some repetition period in different directions. As shown on the top diagram, the repetition period is what user sets. Delta t, the time of flight, must be shorter than the repetition period. Repetition period will increase with the distance that we want to sample. So, to summarize, the repetition period must be greater than time of flight. If we set the repetition period, that sets the maximum distance that one can sample. If it's, say, 100 meters, then there will be corresponding repetition period. If I want to sample up to, say, 300 meters, then repetition period has to be increased, in this case, by a factor of 2. we often talk about frequency, sampling frequency. So frequency is inversely proportional to period. Therefore, Rmax is also inversely proportional to repetition frequency. So now that we understand that there is a maximum distance that one can sample, what about the minimum distance? Suppose that I produce uniform pulses of certain duration, and I do satisfy the condition that the repetition period is longer than the duration. Suppose I have infinite bandwidth in this idealized case, and suppose I have ideal photodetector. In this case, the response of the photodetector, shown below, matches exactly the shape of the light pulse. If my electronic clock can measure delta t, no matter how small it is, then in theory there is no limit on the minimum distance measurable by LiDAR. However, in realistic systems, the bandwidth is not going to be infinite, it's finite, and that is going to affect fidelity of the responses coming from the photodetector. If the repetition period is also set small because I want to have high sampling frequency, a pileup can occur. If the pileup causes the signal to stay above the trigger level, then there will be ambiguity in the measured distance. Therefore, in realistic design, one does expect some limit on the smallest measurable distance. Let's now briefly discuss the maximum sampling rate. Suppose I want to measure or construct 3D map up to a certain distance, let's say 100 meters. What is the fastest rate with which I can sample the scene? And this ignores the time I need to spend in steering the beam from one angular location to another. For 100 meters, one finds that the sampling frequency is about 1.5 megahertz. Let's now discuss the challenges facing an engineer designing time-of-flight LiDAR. But first, let's begin with the wish list. What it is that I would like to be able to do with my LiDAR. It would be highly desirable to be able to construct 3D maps at a distance of 100 meters or more, maybe up to or even 300 meters. I would like to have 360-degree azimuthal coverage. I would like to have perhaps 20-degree declination coverage. I would like to have sampling resolution of 0.2 degrees or so. Please do not confuse this angle, 0.2 degrees, with the diffraction. This is not diffraction. This is angular separation between sample points that sample the 3D scene around me. And I would like this information about the surrounding to be refreshed at the video rate, let's say 20 frames per second. Can I satisfy this wish list? Is it possible? Is it possible to do it with single laser and a single photodetector? To meet the challenge on the previous slide, we need about 3.6 million samplings per second, or 3.6 megahertz sampling frequency. But we just learned that for 100 meters, the best we can do with one light source and one photodetector is about 1.5 megahertz. Not enough. This frequency will fall down as we increase the maximum range that I want to sample. So the conclusion is that one source and one photodetector will not be able to provide us with the requirements or the wishes that I have. Therefore, one needs to compromise and or invent different approaches. In what follows, in the next several slides, or many slides I should say, I'm going to try to convince you that in time-of-flight LiDAR, there are two main challenges. One of them is beam steering. How can I send pulses in different directions? How I can raster the scene around me? That's one challenge. And the second challenge, which I'm going to emphasize more is the photodetector. We are going to see that the photodetector will generally receive a very small amount of returned light. But first, let's look at various considerations. One is light source. Primarily, light source must produce radiation that is safe for human vision. It should produce pulses of short duration. As we learned before, longer pulses may produce larger depth uncertainty. Currently, you can get pulses at the duration of about 2 to 5 nanoseconds, and those pulses must be produced at the high repetition rate. What rate? The one that we learned about in previous slides. Megahertz. It should have high peak power. Again, we're going to see shortly the amount of light returned will generally be very tiny. And so we'd like to pack our pulses with as much power or as much light as possible, provided it's safe for human vision. Time of flight LiDAR must be able to operate under all conditions, including sunlight, which will mean that we will have to have narrow band filters that are going to separate the laser light from the background. And thus, our source must produce light with high spectral purity. Let's now look at the photon budget of time-of-flight LiDAR. In this diagram, the light from the laser comes from the direction shown by the arrow. It strikes the target and reflects from the target. The worst possible reflection for LiDAR is specular reflection. This would occur if the target is highly polished, highly reflective. In this case, very few, if any, photons would get back to our detection system. Fortunately, most surfaces are not mirror-like, and one can expect some degree of Lambertian reflection, which means that photons are going to reflect diffusely, and thus some fraction of these photons will reflect in the direction illustrated by the cone, which will be then detected by detection optics represented by area A sub 0. These photons traveling in this cone are the photons that I have ability to perhaps detect. Let's dwell on this point a little bit more and discuss the photon budget from the point of view of LiDAR equation. There are several variations of the LiDAR equation. Here is a simplified form. On the left-hand side, we have power received for a distance r. And that power received will depend on the power or peak power we emit. Will depend on target reflectivity. Will depend on the collection area of our collection optics. And please note that there is an inverse r-squared dependence on the distance, which means that the received power rapidly decreases as inverse r-squared as the target is further and further away. Another factor is transmission of the optics. And another factor, gamma here, is atmospheric extinction, which is a variable. It will depend, for example, on weather conditions. And there's another r in the exponent. To get an idea of the photon budget, let's look at this figure from Williams 2017. It shows the number of photons received as a function of range for a variety of pulses with variety of energy using 1550 nanometer light and some reasonable parameters for the LiDAR equation. Just to give you an idea, a 50 nanojoules pulse of 4 nanosecond duration corresponds to 12.5 watts, and it contains about 10 to 20 photons. Please look at the figure where you can see that for 100-meter distance, the number of photons that we get will range from few hundred to perhaps few thousand to maybe few tens of thousands. Even in that optimistic case of few tens of thousands, this is just a tiny, tiny fraction of the number of photons that were actually emitted in the single pole. Photon starvation is to be expected in time of flight LiDAR. Whether detection is made or not ultimately depends on the signal-to-noise ratio of the detection. Suppose that our detection consists of avalanche photodiode, which is up to now the most commonly used photodetector in time of flight LiDAR. And our electronics is going to be a resistor whose role is to convert current from the APD to voltage, which is then subsequently processed. For this electronic system, one can find that the signal to noise is equal to, well, in the numerator, that is effectively the signal. In the denominator, I have summation of noises. Those can be divided into several. We have photon shot noise. We have background photon shot noise. We have dark current shot noise. And then finally, this is Johnson noise that comes from the electronics, from the resistor. Below is the legend of the various terms in the equation, but those in blue, like detector's gain, detector's excess noise factor, and background light optical power, are the items I'm going to focus or discuss in somewhat greater depth in the following slides. But for detection to be made, that signal to noise must be greater than 1. However, a signal to noise of, let's say, 2 is still very poor. The uncertainties will be large in the distance. And so higher this number, better it is. One should expect, or one should strive for signal to noise to be on the order of 10 or higher for detection to become reliable. Before we discuss those items marked in blue, let's now consider another challenge or another possible choice an engineer must make. And that is what wavelength to use. There are a number of wavelengths under consideration by various groups designing this system. But many of those wavelengths are going to be either 1550 or 905 or close to them. And so let me now discuss the choice between the two. Should I use 1550 or 905? There are pros and cons for each one. Let's begin with 1550. The big plus for this wavelength is that it is best for eye safety. One can pack the pulses with a great deal of power and be still relatively safe when it comes to human vision. As I'm going to show shortly, the solar background is also lower at 1550, which is another plus, which means that there's a lower background, photonic background in this wavelength. However, the disadvantage of 1550 is that it requires infrared photodetectors, mainly silicon-based photodetectors do not operate at this wavelength. Infrared detectors are generally more expensive, and they do have higher dark currents. 905, surprisingly, it has better transmission in the atmosphere, especially when moisture is involved. However, the great advantage is that one can use silicon-based photodetectors, which in comparison are less expensive. So now let's look at the photonic background, the light that is undesirable, that you have to somehow shield or protect from. This is solar spectral irradiance at some sea level location as a function of wavelength. Please note that this specific spectrum will vary depending on location, depending on weather conditions. So think of this as sort of representative. The figure is from Maxim et al., 1983. One can see that solar irradiance is higher at 905 than it is at 1550. So this would favor 1550, i.e. the background, the photonic background, is smaller at 1550. However, let's look now at another factor here, which is absorption coefficient of water as a function of wavelength. Earth is a water planet. There's always moisture in the air, and generally reflected surfaces are going to be moist as well. This figure from Wojciechowski et al. 2014 shows that absorption coefficient of water at 905 is lower, almost by a factor of 100, than absorption coefficient at 1550. This causes 905 light to have better transmission through the atmosphere, and generally there will be a better reflection from wet surfaces. As shown by this figure, again adopted from Wojciechowski et al. 2014, the figure shows reflectivity for two materials, brass and concrete. The solid line corresponds to dry surface, whereas dashed corresponds to wet surface. In case of brass especially, one can see that when it's dry, it reflects better at 1550 than 905. However, when it's wet, its reflectivity drops substantially compared to 905. So these properties would now favor 905 nanometers. Let's now discuss the properties of photodetector that one desires for time of flight LiDAR. First, one would like to have high photosensitivity, which I could also state as wanting high quantum efficiency. We would like to have high intrinsic gain in the photodetector. Please, this should not be confused with the gain of amplifier. Amplifier cannot increase signal to noise. So we are talking about the gain, intrinsic gain of the photodetector. It should have small jitter and should have small excess noise. Let's quickly discuss some of these properties. Jitter. Jitter is variation in response time. If I illuminate photodetector with bursts of light, as it would be the case in LiDAR, the response time is going to vary from event to event. The variation in this response time is called jitter. A jitter of about 100 picoseconds would imply depth uncertainty of about 1.5 centimeters. Higher jitter will then imply greater uncertainty. This slide shows the importance of intrinsic gain in the photodetector. At the bottom, suppose I have a photodetector with no gain, like photodiode. It's illuminated by light, a pulse of light. At the output of the photodiode, I get signal in the form of current, and perhaps it looks as the plot in the top left corner, noise, 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 signal, noise. However, this signal must be sampled with electronics. For example, the resistor that we saw some slides ago. The electronics has noise. Therefore, what one ultimately sees is sort of convolution of the output from the photodetector and electronics noise. As a result, one can get output as shown in the top right corner of this slide. Is there a signal there? Well, we all know that there is because we are discussing it. But if I just showed you that plot alone, the top left right corner, would you be certain that there is a signal? Maybe not. But suppose now I have a photodetector that does have intrinsic gain. So what I did here to construct the plot on the left-hand side is take the plot from the previous slide and just increase everything by some factor, maybe 4 or 5. But now this output from the photodetector is convoluted with electronic noise. And here we clearly see that there is an output signal. It is the intrinsic gain here in the photodetector that made photodetection possible. Let's now briefly discuss the importance of excess noise. Excess noise, in some sense, is the penalty we have to pay for having gain. It arises when gain exhibits variation. We often express excess noise in the form of excess noise factor S. What we see here are two waveforms, which are due to the same amount of light, but because of gain variation. Waveform 1 is bigger than waveform 2. If I have a fixed trigger then this variation in height will translate into error in measuring the time of flight. This could be circumvented by having constant fraction trigger, but such triggering requires more sophisticated electronics. If we don't have that, then one can conclude that excess noise is going to add uncertainty in measuring the time of flight, and thus will create uncertainty in the measured distance. The most commonly photodetector used so far is avalanche photodiode that operates in the linear mode. Its gain is up to about 100 or so. This is an okay gain. It's not great, but certainly it's more than one. One great advantage of APD is that it has high quantum efficiency, and I should point out that APDs can be made of silicon, but also of infrared materials. So APDs can be used both at 905 and 1550. One disadvantage of APD that it has large excess noise. Ideally, in perfect world, excess noise would be 1, which means no variation. Bigger the F number is, worse the variations. In case of APD, the excess noise will range on the order of 3 or 4. This is quite high. However, in the mid-90s, a new photodetector was developed, referred to as silicon photomultiplier. This photodetector has some highly desirable properties that could make it, perhaps, detector of choice in time of flight LiDAR. Very briefly, silicon photomultiplier consists of microcells, but it's not an imaging device. It's not like CCD. Each microcell is an avalanche photodiode operating in Geiger mode, connected in series with so-called quenching resistor. All these microcells are connected in parallel. Thus, there is only one output node where the current pulses are summed up. This silicon photomultiplier, as I said, has some properties that perhaps will make it highly desirable in this type of design. Here I'd like to show you some figures from Hamamatsu, which is manufacturers, one of many, or one of some of these detectors. Here I'd like to point out that Hamamatsu does not make systems, LiDAR systems, but it makes components that could be used in such systems. So first, on the left-hand side, we see a plot of gain as a function, effectively, of bias voltage. And we can see that the gain for typical biasing voltages will be on the order of 10 to 5 to 10 to 6. So it's a gain of about 1 million versus maximum 100 for APD. But most importantly, the excess noise for this gain is only about 1.3 or so, sometimes even less. So this is a huge improvement from the performance of avalanche photodiode. The original silicon photomultipliers were primarily developed for PET, positron emission tomography, which operates around 400, 500 nanometers. Our new designs, as shown on the plot on the right-hand side, have increased sensitivity at progressively longer wavelengths. So what we see here is a plot of photon detection efficiency, which is really a probability of photon detection as a function of wavelength. At 905, that probability is on the order of 7-8%. I do know that this is not great. However, this sensitivity is likely to increase with future generations of silicon photomultiplier. Currently, SiPM cannot operate in 1550. However, it is very likely that these detectors are going to be developed using infrared materials as well. Let's quickly go over two additional figures. One is amplitude versus recovery time. And so when a silicon photomultiplier is illuminated with a burst of photons, there's some time necessary for the microcells to come back to so-called ready state. We can see that the recovery time is on the order of few tenths of nanoseconds. This should not be an issue in time-of-flight LiDAR, where repetition rates are going to be, or repetition periods are going to be much longer than this recovery time. And finally, the plot on the right-hand side shows output current as a function of light level. And so here we see linearity. And linearity in this device depends on number of microcells and can deteriorate at high light levels. But as I discussed in this presentation, it is the photon starvation that is more likely to be an issue than too many photons.
Oh, you can actually, if you would like to watch, actually.
Let's now discuss the various designs of LiDAR. But please know that all those designs are going to be time of flight at their nature. As I discussed, there are two challenges in time of flight LiDAR. One is beam steering, and another one is photodetector. In the sequence of next few slides, I'm mostly going to discuss or address beam steering. Here we see probably one of the simplest designs, a mechanical design, mechanical LiDAR. It consists of 64 channels. You have 64 beams where pulses are emitted like spray-like manner because these beams rotate, as you can see on the top of the car, at certain rates, 5 to 20 hertz. Each channel has dedicated photodetector, avalanche photodiode. And so one can scan the scene and produce the 3D maps. Such LiDARs already do exist, again, as the picture indicates. A variant of this idea is rotating mirror, where a mirror with 8 sides, each side is a mirror with slightly different angle, tilt angle, rotates at certain rate, and it's illuminated by pulses from a laser diode. And these pulses are sprayed in a strip-like manner, i.e. rastering the scene. In this case, one must have not just one, but array of photodetectors, as shown here. These could be APDs or could be SPAD, could be a SPAD array. Due to shortness of time and different focus, I'm not going to discuss SPAD in this webinar. And here we see a reference from Nicholas et al. Who demonstrate feasibility of this design. So at the top we see a 3D map in full daylight. The sensors used was SPAD. The rate of information is 10 frames per second with a field of view 55 by 9. So these are working designs. Their great advantage is that they are simple in concept, but one disadvantage, undesirable feature, is that they're moving. There's rotation. There are moving parts, and driving is a rough environment, so that when there's rotation, there's motion, there's potential for failure. And so there's a desire to create beam steering where there's as little motion as possible. And so one step is to use MEMS mirrors that would raster the scene. A MEMS mirror, or mirrors, could be a mirror array, is a tiny mirror whose orientation can be controlled both in horizontal or X and Y direction by applying electromagnetic forces. So, depending on orientation of the mirror, the pulse is going to be sent in different angular direction. Please note that in what angle, in what direction the pulse is sent must be known and must be synchronized. We must be aware where those pulses are going. One concern in mechanical LiDARs and mirrors is that when the pulse is interacting with reflecting surface, there will be divergence introduced. And we already learned in this webinar that pulse or beam divergence is highly undesirable. That divergence may limit the number of resolvable spots, and also is going to worsen the photon budget. Another idea, which again is time of flight LiDAR, is so-called flash LiDAR. In this case, the scene is not rastered, but instead flooded with photons. And so illumination optics produces a pulse that illuminates some area of the target. That area must be matched with the field of view of two-dimensional array. Again, in this array, every element must be able to measure time of flight to the point of the scene that it is imaging. And so in this design, I can measure distance to the point that reflected the light. In this case, the resolution is limited or affected primarily by the size of these detecting pixels in the imaging array. In this design, there are truly no moving parts. However, one disadvantage is severe photon starvation when the distance goes beyond several tens of meters. And so right now, there are no practical designs of such flash LiDAR, say for maximum distance of 200 or 300 meters. This may improve with time, but it does not exist at this moment. Another interesting idea exploited is the optical phase array. Again, this is all about beam steering, sending beams in different directions. Optical phase array consists of pixels, where each pixel, when it receives light, coherent light from illumination fiber, that pixel can re-emit this light with different amplitude and different phase. These amplitudes and phases can be electronically controlled. As a result, in a far field, for a given pattern of amplitudes and phases, one can create different illumination patterns. As shown in this slide, this is from the reference Abedassi and Hashem in 2015. So again, depending how I control those pixels electronically, I can create patterns like single beams or structured light or other patterns as well. There are truly no moving parts. However, some disadvantages is that because the pixels are quite or much larger than the size or the wavelength of light, the beams, for example, like in this case, will still have rather large divergence. And also, the system has rather large RC constant, which means that changing the direction of the beam or changing the patterns is still quite slow. So, at this point, I hope that I've convinced most of you that designing a working time-of-flight LiDAR at a reasonable cost is very challenging. If it were not challenging, you already would have such LiDAR, and you would not be listening to me because there would be no point of doing that. So it's inherently difficult. Sometimes it's good to step sort of back and think perhaps about other approaches. And so in the remaining 5 or 10 minutes, I would like to introduce an alternative approach to time-of-flight LiDAR. This one I'm going to call frequency modulated continuous wave LiDAR. The idea comes from a radar where this approach has been used for a long time already. It's well known. But first, due to shortness of time, let me begin by advantages of this approach. So I'm going to show you quickly that in this type of LiDAR, we may have actually photon sharp noise limited detection, which will mean that we may be able to use photodiodes and not necessarily avalanche photodiodes or silicon photomultipliers, so less expensive detection. This approach is immune to photon background, so it won't matter whether we are driving during the day or at night. Another advantage is that the distance and velocity information is in the frequency domain. Another advantage is that the electronics required for this detection will have generally lower bandwidth, which will mean a lower amount of noise. Of course, there are some disadvantages. But first, this is not truly continuous wave. We still have to have pulses if we want to raster the scene. However, these pulses are going to be of much longer duration, say microseconds instead of nanoseconds. And this approach generally will be more computational heavy. So let me now go, since I have only about 5 minutes left, let me just go through the basic concept of this approach. We produce a continuous wave. However, the frequency, in this case frequency of light, will be modulated, chirp, so the chirp modulation. And we are going to start with some frequency base f sub 0, increase the frequency to f max. That change is referred to as bandwidth, and that change will take place in this amount of time t. And then we go back to frequency f sub 0, and again f max, f sub 0. So this is known as chirp modulation. The basic idea, as I will show in later slides in greater detail, is to compare frequency of the local oscillator, which in this graph is shown with the solid line, with the frequency that was returned from the target, shown by the dashed line. At a given moment, frequencies are going to be different. One can measure this difference. This will be a beat frequency, SB1 on the left-hand side and SB2 on the right-hand side. The shifts that you can see, the horizontal and vertical, are going to be due to the time of flight delta t. That gives the horizontal shift. And then there is a vertical shift due to radial velocity of the target. This frequency, SB1 or SB2, will be well within electronic ability to measure. It's going to be much lower than the frequency of light, which of course one cannot measure with any photodetector. There are some trade-offs involved in this approach. Very quickly, larger the bandwidth for a given period, better the resolution, and for a given bandwidth, smaller the period of chirping, better the resolution. The basic design of heterodyne approach with optical mixing is as follows. I have a laser whose output frequency can be changed. If that's not available, there are optical systems where I can change or chirp the frequency. It emits beam of light. Some of the light is siphoned by this combination of mirrors, and this light is going to serve as a local oscillator. The rest of the light goes to the target. Before we send it to the target, we often apply an offset in the frequency, and that's to remove ambiguity in the sign of radial velocity. The light comes back, and then is made to interfere on the surface of the photodetector. That interference is going to produce DC signal plus an AC signal. It is the AC signal whose frequency will contain information, or will contain the beat frequencies from which we can then obtain distance and the radial velocity. There's a little bit of math here, but the basic idea is that when I mix the returned light and local oscillating light, it is the electric field of those beams that combine as vectors, and what I measure is the square of that sum. As a result, the photodetector here is going to produce current that has two DC components. They are of no use, there is no information there. But then I have AC part. That AC part contains the beat frequency, which contains information about distance and radial velocity. But please note, the amplitude of this AC part depends on intensity of local oscillator and the return signal, which means that we have amplification. If I have enough light in the local oscillator, I can drive this amplitude so high that I amplify effectively the return signal. This is a great advantage of this approach. For the detection to be optimal, it is necessary to optimally overlap the beams. There are some conditions that must be met. The beams should have the same polarization and spatial coherence. So, as mentioned already, the great advantage is that the signal to noise here, represented as ratio of powers, can become photon shot noise limited, which means that this is the best possible signal to noise I can get. There are some undesirable features that can be rectified with so-called balance detection. If the local oscillator has some excess noise, then that may contribute to worsening of the signal to noise. To eliminate this concern, one can use so-called balance detection, where the signal beam and local oscillator are split 50-50 and detected with balanced photodiodes. To make this long story short, this detection will completely remove the DC parts and any variation in them, thus improving the signal to noise. I would like to point out that Hamamatsu, which I represent, manufactures, in addition to silicon photomultipliers and many other photodetectors, it also produces balanced photodiodes that come as modules, or one can buy or use matched bare photodiodes. This concept does work, as exemplified by reference Gao and Hui 2012, which showed that one can detect with great certainty, in this case, a distance of 20 meters. You may say, well, that's not a very long distance, but I would like to point out that this paper is primarily concerned with how to modulate the signal, rather how large or small distances one can measure. So this is definitely a working example. So it's time now to wind down this presentation. And so let's ask the question, is there a perfect LiDAR? And of course the answer is no, not yet. All the designs that we discussed will have some pros and cons, and we have to, as engineers and scientists, sort them out and come back with the best solution. However, at least in my mind, it is certain that some form of LiDAR will be necessary on the future self-driving car. Let me briefly summarize this presentation. As I said, some form of LiDAR is likely to be needed on self-driving car. Time of Flight LiDAR is very challenging to design. Beam steering and photo detection are the most outstanding challenges. There's a growing interest in frequency modulated continuous wave LiDAR with optical mixing. I should point out that other designs are possible. You could modulate amplitude, you could modulate phase, you could also have electrical mixing. So this is not the only way to have to have information in the frequency or phase space. And there is no default LiDAR design yet. Work is in progress. Before I formally thank you and conclude this webinar, I would like to bring to your attention some upcoming webinar. One will be presented by me on silicon photomultiplier in January. Also, I would like to make you aware that Hamamatsu is going to be presenting various talks at Photonics West in San Francisco of next year. Also, we are going to be present at booth 521. And so in these events, we are going to talk about the various detectors like SPADs, MPPCs, or silicon photomultipliers, in this case, indium gallium arsenide, so the new sort of family of these detectors. I'm going to give some presentations on spectroscopy, silicon photomultipliers, and PMTs. I would like to thank everyone for listening to this webinar. Again, the speaker was Slawomir Piatek. Below is the information, contact information. If you have any questions concerning LiDAR, photodetectors, please direct them to Mr. Jake Lee at Hamamatsu Corporation. Again, thank you very much, and I now I transfer your attention to Christopher. Thank you very much again.
Thank you, Slawomir, for the presentation. Before we close down, we do have 3 follow-up questions for our audience. So if you can please take 10 seconds per slide and then provide your input. First question is, what do you think about the content of this webinar presentation? The next question we have is, what other topics would be of interest to you for a future seminar/webinar? And finally, what do you believe is an acceptable target price for a complete high-resolution LiDAR system? Okay, that was it for this time, everyone. Thank you for attending this webinar by Hamamatsu, and we'll see you next time.